Good morning. We'll be talking about SIEM correlation and expert knowledge. I'm Stanislav Antonov, Head of Technology Development at Positive Technologies. I'll talk about the correlator itself and how it works. And Mikhail Maximov, a lead expert with us, who's responsible for expertise development. He'll share with you the more practical scenarios of how we develop and how we address practical problems. And I want to get to know you a little bit. Who's in the audience? Do we have more developers or more experts? Can please experts raise their hands if you are here? Experts in what? In cybersecurity? Okay, so it turns out that the others are developers. Developers, please raise your hands. Yes, it seems that we have more developers here today. Awesome. Okay, so what do we call a correlator and what problem does it solve? Most of our products take as inputs a flow of events. And the expert's problem is to single out cybersecurity events from this flow that help us detect that some vulnerability is being exploited. Ilya, in a previous presentation, talked about brute force, and it's a good example of a correlation chain. When first we need to identify a number of unsuccessful events, and suddenly there's a successful event with correct authorization under a certain user. So here we want to, first of all, record a security incident for security guys to analyze, and to apply some mitigators, such as, for example, to block a particular user. To address the problem of looking for chains effectively, we need to prepare the input events. We need to usually normalize them, that is, to bring them to a regular format. And often, for us, is the most expensive task in terms of performance. That's data preparation. Second, we need to add additional information to data that we have, to enrich data, such as, for example, match identifiers with names, or to check which strings are domain controllers, or to label the users into those who have admin privileges and those who don't. For experts to be able to introduce their expertise into the product, they need a rules language, a DSL. And it seems that I will be repeating from Ilya's presentation in certain aspects. So we need to provide a DSL to experts to create a language which they could use to write rules, explaining and providing their expertise in a form that is understandable by the product. Rules are also written by integrators that implement the product for a particular user, for a particular software, a particular environment. Customer-specific security tools, or EDI, electronic documents interchange, or whatever. And thank you to the questions to the previous speaker. We have to develop SDKs for those aspects. With our own in-house experts, we might sort of be lazy sometimes and not do it. But when we, for the integrators to write rules, they have to have means to do that. And sometimes experts would even have to write their own SDKs or IDEs. Rules also have to be tuned. The problem is that many rules require additional information to work correctly in the customer's environment. If a user starts editing rules on their own, we lose the opportunity to provide out-of-the-box expertise to them. And at an update, users would have to continuously update the rules, rewriting them for their own needs. That means that we've got to provide external information to the rules. And there have been various attempts to provide this to SIEM solutions. Perhaps the earliest one is the so-called active lists. In those times, that was the simplest solution, with collections with certain parameters. Users could modify those collections, add data, remove something, write exception rules, or users who had admin privileges. And that was a very simple tool. The second scenario that we developed, because we integrated SIEM with Max Patrol, we had to provide information about the assets into the correlator so that it was possible to use them. And so here's how we came with the concept of assets projection. What are assets? Those are node representations in a tree shape, and assets projection helped convert some information about the assets into Mongo formats and to provide to the correlator information or access to this data. This was a usable approach. We have used it for several years, and thereafter we went to a more practical and quick solution. We integrated the correlator into PTA. Leonid Yuriev is responsible for DBX development, and you can check out the repository, or you can check out his presentation at Payloads. I guess it was in 2017. This helped us implement quite a quick and high-performing mechanism of table-based lists, which completely user customizable, and by users I mean experts. They can write both elements of the list, they can write indexation, and they can write very smart exceptions from the rules. Table-based lists are used by the correlator not just in the read mode, but also in the write mode. We can give an expert the opportunity to save certain information from events and to later refer to them. And this is perhaps the most exciting slide. The structure of our correlator now and the structure of the rule. Ilya said that we don't have a name for the rules. Well, the main DSL that we have is called XP, that is extraction and processing. Surrounding it, there are a few other DSLs that help express various parts of the pipeline. This is a sample correlation rule, and the structure of our current correlator. I guess this is a snapshot of what we had some 2 years ago. So first, we describe the representation of the event itself. And it's important to express the filter here, to very accurately describe the event filter. This filter works in the pipeline at the router, and we can describe multiple types of events. In a brute force scenario, for example, we can express that an event that is a failed access attempt, a successful access attempt, and those events would be labeled at the router, and there will be an idea of which thread of the correlator they are supposed to go to, so that an instance was formed out of that. After the events go into the worker modules, we start having a chain assembly. With brute force, for example, the key could be the user login or the sequence of the username and the nodes which it visited or the service which it visited. So then, based on that key, a set of events is being formed, and based on the rule description, a chain is built. When the chain has been built, it goes into the renderer, and the output correlation rule is formed. And there's a description of what data has to be taken from the event, what data has to be put into the table-based list, and what information has to be included into the alert to be sent to the business system. Here we can see a few points regarding the correlator optimization, such as a separate event cache. Why do we need it here? Well, in the process of execution for large event flows, we can get quite a number of instances concurrently. We have to be very efficient with memory in the correlator and maintain the speed of processing. So many actions we try to postpone until the time that the chain is built. The worker module of the correlator to calculate chains only needs the types of events and their timestamps. There are some details related to certain chains. We might need some additional keys to infer that certain events have certain attributes, such as, for example, with a pen test, we need to understand that requests go to various services. And now, when we reuse the correlator in multiple products, the correlator must be resilient to various scenarios. In a larger system such as SIEM, you have quite a lot of hardware and high-performance flows, but there might be other scenarios as well. And if the router and the correlator are normally separate processes, but in other products it could be one process that uses the same DSLs, the same rules. Here's how a correlator works in our product Max Patrol SIEM. And you can see that there are other entities, business entities, around the processing engine. And the engine are analyzer, enricher, resolver, and router and correlator. But there are other add-ons, such as a resolver. And this is what helps link events to Max Patrol logic. That is the business entity, which is not very much linked to other parts of the process. There's also the notifier that can convert the alerts from the notifier into max patrol events. This is, again, business specific. Not all products need this. But things such as normalizer and a correlator, they are used in various PT products using the same DSLs. And we can see some finer details here and some problems that we might come across because of the quality of expertise that the customer might have. Because events generated by the correlator are fed back into the pipeline so that the experts could build correlation chains. Clearly, there are scenarios that could use to a system overflow with those events. A bad correlation rule may result in a cycle with continuous event generation, and you've got to know how to protect against that. With SIEM, we have tools that automatically disable rules that generate too many incidents. And that is, again, a business-specific thing that is not linked to the engine itself. Now let's talk about where and why correlators and engines with our DSLs are used. On top of SIEM, the normalization and correlation processes are actively used in SIEM and XDR. They were also released as standalone modules in the Solder open projects, and they are also used in Sandbox. In WAF, I think only aggregation is used from our engine. The fact that we have expertise on correlation, we were able to launch the new product, XDR, by reusing in it some of the expertise. It reuses a lot of the same rules that initially were written for SIEM. We also can reuse the same tools for writing and testing normalization and correlation in different products. And I guess with this, I'll hand it over to Mikhail now. Good morning. Let us go back to our conveyor belt or process. And let's see which rules we can write for the services in this conveyor belt. I've singled out here the two types of rules that we'll discuss. And I also singled out on this slide the table-based lists because they're very important for the rules of correlation and enrichment. And this is through which experts can provide their expertise. But before we go to rules analysis, let's talk about event description process. This is the view into which raw events are converted. And the initial idea was the common event expression with some amendments. The first versions of this process were entities where each entity had its own attributes and some classifying values that described objects and actions on those objects. As we evolved, we started describing new entities because we saw that the entities that were described in the common event expression approach were not sufficient for us. And then we came up with the database that we had at that time, and we saw that the process becomes very cumbersome. And we noticed that most of entities are not used in a specific event description. Only a small number of attributes would be used in any given description. And we also noticed that there were some duplication of attributes in various entities. So we decided to revise the approach to event description, and we identified two key entities with attributes, the actor and the object, the subject and the object. And now we describe events in the form that the subject performed a certain action on the object. And the classification into the subject or the object determines the fields. We also identified separate entities for network interaction for the source of event, because often the source of the event is not a participant of the interaction. It is rather in an observer role. And also a set of separate attributes that experts also needed. This helped us reduce the number of fields quite substantially while not losing out on the features, on the functionality. And to expand descriptions on the subjects and the objects without adding additional attributes. Clearly, as our expertise grew, as the scenarios that we had to tackle became more and more sophisticated, we made amendments, but not as radically as at the early stages of our approach. Let us now go to the rules themselves. Let's start with the normalization rules. And the XP language underlies all of our rules. Normalization rules consist of two components. First is preliminary parsing of an event and checking for meeting the selection conditions. And if this condition is met, then the next part is the main rule and transformation of the data into the necessary format. Let's look at a simple example of a rule using our DSL. This is a text log from an Nginx source, which tells us that connection was closed. To parse this log, we use the text string. And the components there are classifier tokens that help us match the variable parts of the log and some anchors or text constants, which help us match rules to certain event segments. We can also see optionality tokens reflected with a question mark. That's when some of the events are optional, depending on external factors, and we can implement such an optionality. Or we could provide options in parsing using a vertical line. If after the initial parsing no further data processing is required, we can save the fields of the normalized event right from the format string. Or if additional processing is required, we can save temporary variables and then do the processing within the main text of the rule. Here we have a very elementary processing. To describe the reason why the event happens, we only need to drop the non-necessary symbols. On the right, you can see how a normalized event looks like in the description of our process. Further on the code of this formula, there is this identifier ID. Many confuse this with the rule identifier, but this is actually the event identifier, because one and the same rule can parse various types of events. And the reason is because the source generates events of various types, but which are very close in their composition, with only some sections of the events being different. And we can write a universal formula that would process the whole variety of such events. and to use conditional operators inside the rule to analyze the subtleties of the values. Let us look at other examples of how we can parse the data with our DSL. Often we come across an event that contains various formats. That could be a text log that has within itself a JSON structure, or as in the example here, a structural event, which is in a table format that's a flat JSON, which has within it an XML structure. To conveniently parse such logs, we have a mechanism of nested rules. Using keywords subformula and end subformula, we describe a section of this rule. And using this submessage function, we do a call of this nested rule by giving it as an input the part of the log that we want to process with this rule. And you can see this cond, which is additional condition filtration to select the events of interest. The next example shows various options of data filtration. Here we convert the timestamp to the required format, and we build a string out of the various elements of the event to describe the reason why this event happened. This would simplify for the operator the understanding of why the event happened, rather than having to look at the various separate elements of that reason. And the third example is how you can use the conditional switch case operator to map the various the importance of the events that the source operates with to the importance metric of our system, and some statistics on how many normalization rules we have in our products. Currently, the number of rules is in excess of 7,500, and this number of rules is covered by more than 17,000 tests. Let us now go to correlation rules. This is a brief overview in block structure of what they consist of. First is queries to table-based lists and filters, the description of the target chain and time intervals within which we expect to see that chain. Once there's a successful match of the chain, processing of the source event happens, and the development of the output correlated event. And finally, there's operations with table-based lists. We can add some records to the table-based lists, we can remove some records, and we can also clean those lists on certain conditions, based on certain conditions. Let's look at an example. Let's start with a simple case where we want to detect a creation and deletion of an account in a short period of time. Here we will need just two events, and we'll look at a Windows-specific example. For Windows, we will be looking for events based on message ID that is characteristic for that source. And let's look at the key structure here. That is the key that groups events into one instance. Importantly, what matters for us is the values of those fields and their sequence. The names of the fields are not important to build a key. Here we look at the node where the events happened and the account name, which is being created and then deleted.
An interesting construct is filter, an interesting word. In the product, you can select pieces of filters into a separate object and then reuse them in as many rules as you like. Now we use our standard filter, not from correlator, in order to avoid cycling, because there were such cases. And we say that by filtering, we're interested only in the events which come from the source. All others are not interesting. Then exceptions mechanism, I'm not showing it to you. It's queries to blacklists, whitelists, and checking the values there. We describe the case which we are interested in now. We have to describe the chain of events and its temporal intervals, how to create and delete accounts fast. So time interval is 1 hour. We have several operators here. We have the parameter which describes the chain, no, not this way, which describe the fixed number of events in the chain. We are expecting 2 events. As soon as those 2 events takes place, we shift to processing and building the result, the correlated event. It's a simple example. The main task is just to store data and to fill in the correlated event. We take all data from the first event. It's information about the account that was created, the user who created it, and the node where the event took place. The second event gives us information about the user who deleted the account. And in the emit block, we show attack, persistence, local account. Let's look at the second case. It's about the expert of the certificate. If you have the local admin rights. We are interested in 3 events. One of them is absolutely necessary, is the fact of certificate export, message ID 5059, and 2 optional events, launch certutil to export certificate and access to the general access area, which is used for certificate export. We use a macros which was written by our experts, and we send the name of the exe file to that macros and check online of the process the availability of the backup key. In the second event, which is already optional, we are interested in PFX files. The key is simple. We match the events by the host where they took place. Now the chain. Since we have only 1 necessary effect and 2 are optional, 1 mandatory, 2 optional ones, we just link all the filters and identify the time interval through the timer. Timer shows us the number of time, and it doesn't close the event when all the information comes. So if optional events take place after the mandatory one, so we shall have the time to collect them. So migration is something that we can take the name of the certificate from. We fill importance and correlation time fields. Now, if we noticed certutil utility, we raise the importance of event to high, and start checking the command line for tags that can help us to see which tool launched the utility. If in command line we saw certify, we know for sure that CertSync was launched. CertSync, when certificate is exported, applies a fixed name to that certificate. If we found that indicator, we change the type of event to incident so that security person pay attention to it. Thus, we see that optional events can change the importance level of the correlation event and change some of the values. If we found additionally key of share access, we can take from there information about the hacker, the network address and name of the account. And the last section is emit. We fill in the fields, subject, action, object, and the category of event according to the matrix of micro attacks. Let's regard two more cases without going into detail of filters and processes. Look at the correlation chains only. Case 3 is interested that we have identifiers showing us the number of events we expect, the interval from 0 to 5 or more than 5. Also, we can say that we're interested in one event, and if it comes, we're going to look at it in the first place. So we may have any events. We use timer to have a time limit. Case 4 is interested in the combination of identifier with open top border and keyword with different, which shows us the field that is going to be different. For example, if the event, we have 3 events with the same object value, only one of them will get into instance. The n events which got into the chain within 10 seconds should have different object values. Rules of correlation. We can implement chains of different complexity. We can use cascade correlations because correlated events get back to the pipeline. We can have different cases with different time limits, and we can provide security people with different code samples. It will look like subsets of rules that can be identified by higher level rules. We can also use macroses to reuse the code without generating too many rules. We can also implement logic of any level of complexity within the XP language. We looked at simple elementary cases, but in system content we have a lot of processors where experts develop very complex logic to make the process very informative. Some filters cannot be fit into one slide, even if you use very small characters. And complex queries to table lists, including aggregate functions. Currently, we have more than 700 correlation rules, which are covered by more than 2,000 tests, and we have more than 40 macroses to be reused. A few words about expertise development tools. In the database where we manage rules, apart from editor of the code, there is a construct of correlation rules. which can facilitate the process. You can even enter some code manually and then go from the editor to the text-based rules. We have some utilities as well that help us support the full cycle of testing of the rules without connecting to the main product. So they are completely independent. Such utilities have complete list of auxiliary tools like color codes, automatic adding of fields, classifications, templates, and testing and debugging elements. The first utility is provided in the official set. There is also a plugin that we already talked about, which is developed by the developer community. It contains all the functions and capabilities. It supports debugging and tuning the rule. People answer all the questions quite quickly. If you join the community, if you are interested, please join. That's all for me. Now, questions and answers. And don't forget to evaluate our presentation. Stanislav, Michael, thank you for your large presentation. I have a user type question. Please tell me how the rules are installed onto a server and why does it take more time in comparison to other SIEM solutions? Thank you for your question. Look, as I demonstrated in the pipeline of development, we have several points. For example, a story of table lists. All the services are related to it. And when you install the rules, apart from compilation of the rules, you have to provide that rule to all the services simultaneously. We have a two-phase commit here in order to avoid errors. If the system is loaded, the process will take some time. Thank you. Thank you for the interesting presentation. You said you have the same correlator in different products. So it should support different modes of operations inside the process, outside of the process, in parallel between several servers. So really everything is customized. The same product can be used in different conditions. And secondly, the second question, you showed us a description of the correlation windows or fields, different time limits. Does it mean that you can tune those ranges in the operating memory and in persistent memory? So let me answer the first question first. In the build, we have static libraries, shared libraries, and processes that can host several other processes. Depending on the product, customization can be different, and sometimes rebuilding is necessary. Customization sometimes leads to the situation when we face some inconvenient requirements. If SDR wouldn't be necessary, we would have skipped Windows, but we cannot do that. Second part of your question, yes, truly that is so. I wanted to say that we have to save memory. Each instance occupies memory. It has to be stored for some time, and this is the task of the correlator, to collect the event and build a chain of events. And there is one more problem. Events in the correlator can arrive in the reverse order, and still we must be able to build the correct chain. Data come from different sources, and they are desynchronized by time. So the instance is stored for some time before it is properly closed. And this time is regulated by the timers in the rules. I have one more comment. Efficient storage of chains can be different depending on storing them in memory or in persistent storage, for example, in file. And there can be different algorithms of storage, and you need a balance if you support both. Yes, that is true. Usually we give it to experts and developers because in general we cannot allow ourselves to keep correlation in memory for a week. It's too much. We have to keep data in table lists rather and use them. For example, data about opening of a session. You can put it in the table and checked from time to time in different events. Yes, this is the event within the current session or out of the current session. This is for experts to do, and we truly depend on experts and expertise to maintain high performance in our box products. Thank you. Thank you for the presentation. I have two questions. The first one, as far as I understand, the same physical entity, for example, domain controller, can be an object or a subject. And I didn't quite understand. In your entities, are they linked to the event or are they separate from the event? They are, of course, linked to the event. We described one event here only. Different entities can be objects and subjects. We have different classification values for subject and for object, and depending on the entity in the event, we choose appropriate value. And we keep appropriate fields of the objects, fields of the subject. A user built another user, and we have about two fields. One is the object, the other is the subject. And each of them will have appropriate fields. And the second question is about, well, you said normalization is the most expensive process. Are there any limitations or the figures you can boast about? What is the flow of events per second you can support or consume and digest? Well, actually, the answer largely depends on the hardware. Normalizer is the most expensive in the installations that I saw, but it doesn't have any persistent state. It scales very well, scales up excellently. So it's very difficult to say what is this ceiling. It's not interesting. You better look at the pipeline as such. In SIEM, large installations, well, by documentation, 60K is guaranteed. But there are always some subtleties because it largely depends on the expertise we use and the profile of data flow in the customer, because customers are quite different. I can always collect such data flow which will crush SIEM, even within 60K. So we can invent a rule that will crush the system. Always. It depends on the expertise. And yes, well, it's a difficult philosophical question. Can we protect it against everything? No. We just trust the customer. We trust the customer expertise. In specific implementations, it's important to connect to sources. You have to filter away superficial events. You should take only those events which are relative for security, and this is always a problem. Good morning. Two questions as usual. You mentioned table lists, and both questions are about them. First, you didn't mention events of the audit of state of the table list. It's very useful for administration of any SIEM. Do you support such auditing? Do you generate audit event for table lists? What kind of metrics do you use to evaluate those lists? As far as I understand, as far as I remember, in SIEM we have metrics about addressing table lists, how many, why. Then queries from the rules also provide us with full scan of list. It's important to evaluate performance of the system. Yes, we do have such metrics. What other metrics we have? We have some, but I cannot recall. And the second question, do you support correlation by audit events, audit of table lists? Audit of table lists are just appearing on, I don't know, very soon, in one of the future releases. Thank you. Hi, thanks for the presentation. Sergei Maximenko, Gazinform Service. You said you have the normalization mechanism as EDR. Does it mean that we can generate our own rules that we used without changing EDR, or are there any limitation? That is the first question. Second question is about normalization. Normalization is one of the most complex procedures. You mentioned that you have more than 7,000 and 7,500 even. Well, why you have so few connectors and so many rules? What do you mean by connectors? Well, agents which collect and normalize events and then provide them for normalization, support of the sources. Well, the normalization formula is implemented by the connectors, and we're talking about 7,500. That is true, but in one source, we can support 20 types of events, 20 formulas. That's why the number of normalization formulas can never be equal to the number of sources. But the number of sources is rather wide, I can say, from the box, and we are expanding all the time. We have a special team which does that job continuously without break, looking for new sources, internal and external, Russian and foreign. DDR. Yes, let me add a little bit. Sometimes for one source of data, we can have a whole set of rules, but there are other cases in the SIEM, for example, processing of one protocol can be described in one normalization formula. About XDR, I cannot tell you whether users have access to rule generation. We have such plans, of course. If you look at open source EDR solver, which is developed by the community, we provide our services there, and you can enter your own expertise. I don't know anything else. You said that such capability will appear, and many customers ask you for that. For sure, yes. I don't know when, but it will be available. Thanks. Right now, we have events, protection, attacks. Have you analyzed the numbers? What about human factor? I haven't seen that statistics yet. We had 148 attacks against 35, 20%. Have you got information? No, not yet. I haven't got information. I am not ready to answer. The entire data set will be analyzed after the standoff, which is a usual case. We collect all the data and then analyze it in full. Hi, what about correlation engine? What about retrospective correction? When you generate new rules, can you go back in history retrospectively? Can you look the logs, the data, and check whether we had such chains before or not? In Max Patrol SIEM, we have such part of the product, retro correlator, which does exactly that job. A separate module which goes back in time, looks at the database, collects the data, collects the table lists. So retrospective analysis is supported. Thank you. Well, does it look like that? Yes. We have a node where we raise the entire pipeline, we prepare data about it, and we run it retrospectively from existing database objects.